In this video, I am going to describe a very standard problem in electricity and magnetism, that of the motion of a charged particle of charge q and mass m in what is called crossed uniform electric and magnetic fields. The electric and the magnetic fields here are externally caused. They are uniform, they don't change in space or in time. And when we say they are crossed, what we mean is that they are perpendicular to each other. As you can see in the picture, the electric field is pointing straight up on your screen and the magnetic field is pointing straight out from the screen. We are going to use a coordinate system in which the magnetic field is going to point in the z direction, that is, the direction straight out of the screen has been chosen to be the z direction. The direction which is along the electric field is what we choose to be the y direction of our coordinate system, and that obviously leaves us with this direction to the right as x. Now, typically what we would do is draw this not in a top-on view like this, but with a slightly tilted perspective view to emphasize the three-dimensional character of the situation. So you might typically see a picture which looks like this, where the electric field is pointing straight up, the magnetic field is pointing straight out, but this angle that you see is basically due to perspective, and in the same view, the x, y and the z axis point like this respectively. So what we have is that the electric field here is given by a uniform magnitude E naught times the unit vector in the y direction. And similarly, the magnetic field is given by its magnitude, again uniform, B naught times k hat, the unit vector in the z direction. Now, the motion in this case is dictated by Newton's second law in conjunction with the Lorentz force law. So the basic equation that we have to handle is basically mass times acceleration equals the force, and the force is given by Q times E plus V cross B, where the first term here, Q times E, is the electric force and Q V cross B is the magnetic force acting on the particle. We are going to assume that the charge of the particle is tiny enough that it does not disturb whatever sources are causing the electric and magnetic fields, which is a very standard approximation that we use all the time. And now, before we go any further, let us take a look at a few special cases where we already know the answer. Of course, the most obvious case is where E and B are both 0. In this case, there is no force acting on the particle, and the particle will move with uniform velocity, and of course its actual position will depend on what its initial position and initial velocity are. Now, that's a very trivial case. A slightly less trivial case would be the case where E vector is not 0, but B vector is 0. So, you have only an electric field. In this case, of course, what will happen is that the uniform electric field will cause a uniform acceleration of the charged particle, and the particle is going to move in an arbitrary direction depending on its initial velocity, but it will only accelerate in the y direction. So the x component of the motion and the y component of the motion will be uniform motion, whereas the x and the z component will be uniform motion, whereas the y component, the component along which there is an electric field, will be uniformly accelerated. So that is a case which is pretty simple. Another case that we can talk about, which is also quite simple, is the case where there is no electric field, but there is a magnetic field. And in this case, the result is something we actually know from elementary classes. the magnetic field being a zero work force will not increase the speed of the particle. Of course, there is a force here, so the particle will accelerate, but that means it's going to move in a curved path. And the curved path is one where the force is always perpendicular to the motion, because V and QV cross B are of course always perpendicular. And this is definitely satisfied by a very simple example, the example of circular motion, uniform circular motion to be precise. And so the particle would execute a uniform circular motion with a radius that can be easily calculated from the formula that QVB, the force, must be equal to mass times the acceleration that you need for a particle to go around in a circle of radius r, that is v square by r, and this will give us familiar results that the radius of the path is going to be mv over qb, and the time period for the path to complete a complete cycle is going to be given by 2 pi r by v, which is 2 pi m over qb. This is a definitely interesting result because it tells us that the time taken for the particle to complete a circle will not depend on how fast the particle is moving. It will only depend on the magnetic field strength and the charge to mass ratio of the particle. This leads us to a very important notion that we are going to use again later, that of the cyclotron frequency, the angular frequency or the angular velocity of the particle here, which is 2 pi over t, and that works out to be qb by m. Now, while this is really the angular velocity of the charged particle going round in a circular path, the formal name for this is the cyclotron frequency. Exactly what this has to do with the cyclotron and why do we call this a frequency is a different story, which I'm pretty sure most of you already know. But the all important case is that in such a situation where you have only a magnetic field, a uniform magnetic field, and no electric field, a particle which is initially moving perpendicular to the magnetic field will execute a circle with a given radius, and the circle will be completed by the particle in a time which is independent of the velocity. Now, this of course is when the particle is initially moving perpendicular to the magnetic field. If it were moving initially parallel to the magnetic field, there will be no Lorentz force acting on it. V cross B of course is 0 when V and B are parallel. So the particle is going to then execute uniform motion along the magnetic field direction, that is the z-axis here. Now, this means that for a general initial velocity, which has both a component perpendicular to the magnetic field and one parallel to the magnetic field, the motion will be composed of two pieces. There will be a circular motion perpendicular to the magnetic field, but also a uniform motion along the magnetic field, and so the particle will really move in a helical path. Of course, my drawing here is very poor, so what you should realize is, in my diagram, this is the direction of the magnetic field. The particle will carry out uniform helical motion like this. When you look at this from the top, you will just see the projection, which is just uniform circular motion. Now, these are the two very special cases where we already know the answer. Now, the case that will interest us is the case where you have both electric and magnetic field present. And before we go on to solve this problem in its full mathematical generality, let us try to use physical arguments to understand the motion, at least for one special situation, where you have a charged particle which is initially at rest in such a crossed uniform electric and magnetic fields. So let me draw the electric and magnetic fields again. This is my E direction. This direction pointing straight out of your screen is the magnetic field direction. And you have a charged particle which is initially at rest at a point in this. So let's now try to use physics arguments to understand what the motion is going to be like. Now at the very beginning, there is no magnetic force on this particle because the magnetic force depends on the velocity and there is no velocity to begin with. But there is a force on the particle, of course. The electric field provides a force which is in the upward direction. As a result, initially the particle will be displaced upwards. Now, as it moves upwards, it picks up a velocity in the upward direction, which means in addition to the electric force, you will get a small magnetic force, which by using the standard definition of the cross product, you can easily check, will be to the right to begin with. Now that of course means that the particle will no longer move straight up, it will tilt towards the right. So the path will bend. But the moment the path bends, that means the velocity is no longer purely vertical but at an angle, the magnetic force will also bend. It will keep on being perpendicular to the path, so it will bend slightly downwards now. Now note that as the particle moves up, the electric field does positive work on it. The electric force is in the same direction as the motion of the particle. By the way, in this whole discussion, I am assuming that the charge is positive. If it had been negative, instead of going up, the particle would have started going down and so on. But you can easily figure out what will the result be in such a case. Now, here, what you have is an electric force which is upwards and a magnetic force which is still small but pointing mostly to one side, but there is a small downward component. The presence of this downward component decreases the net upward force, and the sideways component, the component towards the x-axis, makes its horizontal velocity pick up. So this is going to tilt even further. As the particle keeps on going up, note that the upward force is still bigger than the downward component of the magnetic force. So it's still accelerating upwards. The speed picks up. The higher up it goes, the more positive work the electric field does. The magnetic field, remember, as I have stressed before, does no work, so it doesn't have any bearing on the kinetic energy and hence the speed of the particle. So the particle is moving faster, the magnetic force is even larger and is now tilted a bit more. So the magnetic field increases in magnitude as the velocity goes up and is tilting a bit more, which means its downward component increases. So as this goes on, a point arises where the magnetic force has exactly the same downward component as the electric field's force. Sorry, I made a mistake in what I said a while ago. It's not the magnetic field which has a downward component. The field, of course, is uniform, doesn't change. But the magnetic force now has a downward component which is equal to the electric force. Now, at that point, the particle's vertical acceleration becomes exactly 0. But that doesn't mean that the particle stops moving upwards. It has an upward velocity and it will, of course, continue upwards. And as it keeps on climbing, its speed is going to increase further. And as the speed increases further, the magnetic force will grow in magnitude, will tilt further downwards. So for both of these reasons, the downward component of the magnetic force will grow and now will exceed the upward component of the electric force. Once again, I realize that I have been saying field several times, whereas what I really mean is magnetic force. So let me repeat this once again. At this point, for example, the magnetic force is quite large and is tilted quite a lot, so the component in the downward direction is actually bigger than the electric force, which has not changed throughout. So now there is negative acceleration in the vertical direction. The particle slows down in its vertical motion. Of course, we are only talking of the vertical motion here. The magnetic field provides substantial horizontal component at this point, so it's accelerating in the horizontal direction. But as the force tilts, the magnetic field's force becomes more and more vertical, so the horizontal component also keeps on going down. Now, what happens is, there will come a point where the downward force due to the magnetic field, which is larger than the force due to the electric field, will be sufficient to slow down the vertical motion to a halt. That means there will come a point where the particle will reach a maximum distance, maximum height from where it started. By height I mean motion along the y direction, along E. And now that it has reached this point, note that at this point the vertical acceleration does not cease. The vertical acceleration is actually quite large, negative. The magnetic force being pretty large here. We will later see that it's actually twice as big as the electric force at this point. But that is something which will take a bit more calculation to work out. But it is definitely true that at this point the magnetic force will be larger than the electric force, and the magnetic force will be strictly vertical. So there is no horizontal acceleration in this case. After this, because of the larger negative magnetic force component in the downward direction, the particle will start coming down while moving in the horizontal direction. Remember, at this point the horizontal component of the force and hence the acceleration is 0, but it already has a large velocity in the horizontal direction, so it will keep on going in the horizontal direction, but it will also keep on moving down. Now, as it moves down, the magnetic field essentially repeats its behavior in reverse. As the particle moves downwards, it's now doing work against the electric field, or rather the electric field is doing negative work on it, so its energy and hence its speed goes down. The magnitude of the magnetic force goes down, and also it starts to tilt, this time towards the horizontal. So ultimately the vertical component of the magnetic force begins to decrease. At one point the vertical component of the magnetic force exactly becomes equal to that of the electric force, after which the electric field produces larger force, and hence the net acceleration becomes upwards. But since the particle is moving down, an acceleration which is upwards essentially means the particle will keep on slowing down. And by the time it returns back to exactly the same value of y as where it started out from, that is, when it comes back to y equal to 0, the work done by the electric force exactly cancels out the negative work it does in the downward phase, exactly cancels out the work it did during the upward phase, and therefore the particle's kinetic energy back here is the same as what its kinetic energy was here, that is 0. So the particle comes to a halt here. But now that the particle is at halt, it will of course not stay there. Now the magnetic force is exactly 0. The electric force is upwards, is going to start moving upwards again. And the whole process repeats, but it does not go back, it repeats exactly in the same manner. So the particle goes like this, again coming to a halt and again going like this. Of course, my drawing is rather poor. What should happen is the particle should keep on repeating the same set of cycles until it exits the region of uniform electric and magnetic fields. So this is a preview of what kind of motion we will get by solving the equation of motion. It's always good to actually try to understand what the motion is, not just from a mathematical point of view by solving the corresponding differential equation, but rather by using physics arguments. Once we have all this under our belt, we will now go back to the original equation of motion and try to solve the differential equation it gives us and see whether this really replicates the special cases that we have talked about so far. Let us now return to the differential equation of motion. M times A is of course m dv dt, and that in our case of motion of a charged particle in an electric and magnetic field is given by the Lorentz force law. Of course, in our particular example, we have E which is uniform and in the y direction, so E0j, plus V, which of course has all three components, Vxi plus Vyj plus Vzk in general, although we can talk of special cases where one or more of these components are missing, but let's keep it general right now. And B is of course B0 k hat. Now, this gives us the following: Vx I cross k, Vx B0 times I cross k, and I cross k is minus j. Q Vy B0 j cross k, and that's I. And k cross k of course is 0, so there is no further term. So what we have is that the force can be written down in terms of its components as Q Vy B0 I plus Q into E0 minus Vx B0 j. So writing down the left hand side in terms of components, we see that we end up with three differential equations. What are the three? The x component gives us m dvx dt is q b0 by. The y component here gives us m dvy dt equals q times E0 minus Vx B0, and the z component gives us m dvz dt is simply 0. There is no force in the z direction. Now, of these three equations, the last one is the easiest to solve. This of course tells us that Vz is constant, so it's constant at whatever value it started out with. So if the initial components of the velocity are Vx0, Vy0 and Vz0 respectively, Vz will stay Vz0 at all times, and since Vz is dz dt, this can be immediately integrated to give you z equals z0 plus Vz0 times t, where z0 is a z component of the initial position, which we have just assumed for the time being is x0, y0, z0. And let me repeat once again, the initial velocity is Vx0, Vy0, Vz0. So this component of the motion is very easy to understand. It's just uniform motion. So the non-trivial part, the part which is really interesting, are the part which comes out of the x and the y motion. Now, given the fact that we have already seen that q times b0 by m is a cyclotron frequency omega c, we can rewrite these equations with slight amount of reduction in the number of parameters in the form dvx dt is simply omega c times vy, and the y equation gives us dvy dt is, again, if you take the b0 common out of this, you get omega c into E0 by B0 minus Vx. So these are the two ordinary differential equations that we need to solve to figure out the motion of the particle. Of course, once we solve this and have Vx and Vy, we can integrate them further to find x and y. Now, although these are ordinary first order differential equations, there is a complication. The complication simply is that the Vx equation, the differential equation for Vx, has Vy in it, and the differential equation for Vy has Vx in it. So these are what are called coupled first order linear differential equations. It's a coupling which makes these equations slightly difficult to solve. The difficulty is only slight because in this case the coupling is rather simple, and I am going to point out to you two different but equivalent, of course, ways of solving this equation. The first method, the one which we begin with now, is actually pretty simple. All you do is try to end up with dvy dt, which depends on Vx here. And the way to do that is differentiate this equation with respect to time. So you get d2 Vx dt2 equals omega c times dvy dt, and that, when you substitute this back, gives you omega c square E0 by B0 minus Vx. So if I bring everything to one side, we end up with the second derivative of Vx plus omega c square Vx minus E0 by B0 equal to 0. Now, all of you would recognize that this is nothing but the harmonic oscillator equation. But of course, in a harmonic oscillator equation, what is actually sitting in what is being differentiated is actually x, the position, and not the velocity as here. And typically you have omega square x equals 0, at least for the standard simple harmonic oscillator whose equilibrium point is at the origin. You would also recognize almost certainly that this is actually the case of a displaced harmonic oscillator, where the equilibrium position is not at the origin but at E0 by B0. What makes this different is that here the variable is Vx rather than x, the velocity x component rather than position. But that doesn't matter, because as far as mathematics is concerned, identical equations can always be solved identically. The interpretation physically may of course be different. Now here, the fact that you have a constant sitting here may seem to make the problem slightly more complicated. But the very fact that this is a constant, the E0 by B0, makes life very simple for us. All you have to do is to realize that E0 by B0 gives you 0 when you differentiate. So you can replace the second derivative of Vx here by the second derivative of Vx minus E0 by B0. And now this definitely becomes the harmonic oscillator equation, where omega, the frequency, is given by omega c, and x, the variable here, is Vx minus E0 by B0. Now we know what the solution to this equation is. The solution is simply Vx minus E0 by B0 equal to alpha, some constant, times cosine omega ct plus beta, some other constant, times sine omega ct. It is now the turn of these arbitrary constants of integration, alpha and beta. How do we find them out? The answer is pretty simple. You use the initial conditions. The initial condition that we can immediately use is that at t equal to 0, Vx is Vx0. So at t equal to 0, this equation gives me Vx0 minus E0 by B0 is alpha into 1, cos 0 being 1, plus beta into 0, just alpha. So alpha can be immediately found out. Now what about beta? Beta takes a bit more work. To get beta, you would have to differentiate this expression and then put t equal to 0. So to get beta, you would need to know derivative of Vx with a certain time at t equal to 0. Now, what we know is not the derivative, but the value of Vx, the value of Vy and the value of Vz at t equal to 0. That is part of our initial conditions. But if you look at this equation, it will tell you that the value of the derivative of Vx with a certain time is nothing but omega c times Vy. So differentiating this expression with a certain t and then putting t equal to 0 gives us omega c into Vy0 equals minus omega c alpha sine omega c times 0, so that's 0, plus beta omega c cos omega c times 0, so just beta omega c. And cancelling out the omega c from both sides gives us beta is Vy0. So we have found out the expression for Vx as a function of time. By taking the E0 by B0 to the other side, we get Vx as a function of time is given by E0 by B0 plus Vx0 minus E0 by B0 into cosine omega ct plus Vy0 sine omega ct. So in terms of the initial conditions Vx0 and Vy0, and of course the constant parameters of the problem E0 and B0, we have found out an expression for Vx. How do we now find out the expression for Vy? We can definitely repeat the same process by differentiating the equation for Vy and then writing down dVx dt in terms of this to get a differential equation which involves Vy alone. But we don't really need to do that. After all, the argument that we just gave for the initial condition actually works at all times. Vy is simply given by 1 by omega c times the derivative of Vx with respect to time. And now that we have an expression for Vx with respect to time, differentiating that is child's play. So Vy is simply 1 by omega c times the derivative of Vx with respect to time. This gives you 0. This is of course a constant. This will give you minus omega c sine omega ct on differentiation, but division by the omega c will give you minus Vx0 minus E0 by B0 into sine omega ct. And similarly, this will bring an omega c out. On differentiation, this sign will become cos. Division by the omega c to get Vy will give you Vy0 cosine omega ct. Just a check, when you put back t equal to 0 in these expressions, this term goes away. This term becomes Vx0 minus E0 by B0 times 1. Add E0 by B0 to that, you do get Vx equal to Vx0 at t equal to 0. And similarly, it's easy to check that at t equal to 0, Vy becomes simply Vy0. So, at least the initial conditions definitely fit. It's supposed to. After all, we put in the initial conditions in our solution. This is just a check that we have not messed up the calculation. At least, if we had messed up the calculation, the chances are we would not have got the initial conditions right. Now that we have got velocity components as functions of time, finding out position components is absolutely trivial. You can simply just integrate this expression with respect to time to get x. Of course, the integration will lead to an arbitrary constant of integration. Let's call that c for the time being. E0 by B0 simply integrates to this. This one gives you 1 over omega c sine omega ct, and this one gives you minus Vy0 by omega c cos omega ct. How do we find out the constant of integration? Simple. Put in t equal to 0, the value of x then is x0. So you get x0 is equal to c plus this term goes away at t equal to 0. So does this term. You are left with minus Vy0 by omega c. So c is simply x0 or x0 plus Vy0 by omega c, and plugging that back in this expression gives us the final result for the position x component. X is x0. I will leave this term and add it to this, so I will write it later, plus E0 by B0 into t plus Vx0 minus E0 by B0 sine omega ct by omega c plus Vy0 by omega c to 1 minus cosine omega ct. Now how do we find out y? Very similar. You just have to integrate this expression for Vy. Now integrating Vy to get y is actually quite straightforward. The integration works out to be y equal to some constant of integration, let's call that d now, plus Vx0 minus E0 by B0 by omega c into cosine omega ct plus Vy0 by omega c into sine omega ct. What we need to do next is put in the initial condition that at t equal to 0, y is y0 in order to find out the constant d. And that is pretty straightforward. If you put in t equal to 0 in this expression, you get y0 is d plus Vx0 minus E0 by B0 by omega c. So, if you put in the value of d here, what you get is y0 minus this quantity, that's d. And so what we can do is take this common to 1 minus cosine omega ct plus Vy0 by omega c sine omega ct. This is my complete solution to the motion. We have got the velocity components Vx and Vy. We have also got the position components x and y. Of course, in addition to the velocity components in the x and y direction, we also know the velocity component in the z direction. Vz is simply Vz0, and the coordinate in the z direction is that for uniform motion z0 plus Vz0t. So all three coordinates and all three components of velocity are now known completely as a function of time. What we can do next is to demonstrate that these solutions that we had found out actually replicate the special cases that we had talked about before. We will do that, but before we go there, let me show you an alternative way of solving these differential equations. Of course, the dvz dt equal to 0 equation is trivial to solve. We don't really want to talk about that any longer. But we will talk about a different way of solving the equations for Vx and Vy, which will involve a new kind of technique which is actually quite useful for other applications as well. To do this, let us go back to the differential equations that we had for Vx and Vy. And as I had said before, the real problem why these equations, this one and this one, are slightly complicated is that the Vx equation has Vy in it and the Vy equation has Vx in it. We decoupled those equations in the method that we have just outlined by differentiating the first equation and plugging in dvy dt in terms of Vx from the second equation to that, getting an equation which involved Vx and Vx alone. In what follows, we are going to show you another approach to the same problem. Now what we do for this new method is introduce a quantity u which is not a velocity, at least not a real velocity. It's a complex function whose real part is Vx and the imaginary part is Vy. So we now are dealing with a complex valued function of a real variable t. Why are we doing that? That will be clear very soon. Indeed, it will be clear the moment we write down the differential equation for u. So du dt is dvx dt plus I, the square root of minus 1 is of course a constant, times dvy dt. And if we plug in the expressions that we already have, this is omega c vy plus I omega c E naught by B naught minus Vx. Now this seems to complicate matters a bit, but actually it doesn't. Let's see how we can rewrite this so that the equation becomes very easy to solve. If you take the constant term separately and combine the other two terms with the velocity components in them, what you get is the following. If you take minus I omega c common out here, you get Vx, and here 1 over minus I is plus I, so you get plus I Vy, and lo and behold, what you have got is u back here. So the equation becomes I omega c E naught by B naught minus I omega c u. So what we have achieved by introducing this complex function is simply a decoupling of the equations, or frankly a coupling together of the two equations in such a way that you end up with an uncoupled equation, an equation for u which involves only u and other constants. Now this equation is of course very simple to solve, and the easiest way to solve this would be to simply divide both sides by u minus E naught by B naught and multiply through by the differential dt. So you get minus I omega c dt. And now we can do the integration. Now, in this case, you don't even need to write out the constant of integration and work it out separately. You can just plug it in the integration itself. Indeed, we could have done that in the previous cases also. Just to illustrate, let us integrate both sides. When t goes from 0 to a final value of t, now we begin to see that there is a bit of a problem in writing this, simply because t here is a variable of integration, it's a dummy variable, whereas a t in the upper limit is a definite value for t. Best way to handle that, if you want to be mathematically accurate, is to change the dummy variable's name to something else. In this case, we are just calling it t prime. And here, we would do the same thing because we want to start with the complex variable at u0 and end at u. So the dummy variable we will just rename as u prime, and we will say u prime goes from u0 and ends at u. u0 of course is nothing but vx0 plus I vy0. Now this integral integrates rather simply to log of u minus e0 by b0 by u0 minus e0 by b0 is minus I omega c t, which immediately gives us a solution for u. u works out to be E0 by B0, where I've just moved this to the other side, plus u0 minus E0 by B0 e to the power minus I omega ct. And that's it. We have found out our solution for the velocities. Of course, it will take a bit more work to figure out Vx and Vy from here, but all you have to do is figure out the real part of this expression and its imaginary part, and in one go you will have found out Vx and Vy. Well, as far as positions are concerned, you could of course find out Vx and Vy first and integrate to find out x and y as we have done before, or you could simply integrate this u to get basically x plus iy, and once again you could actually throw in the initial conditions, so you will get integral of u is actually x plus iy minus x0 plus iy0 equals E0 by B0t, which is the integral of this from t equal to 0 of dt from t equal to 0 to t equal to t, or dt prime from t prime equals 0 to t prime equals t. And if we do the same thing here, you will get u0 minus e0 by b0 by I omega c into 1 minus e to the minus I omega ct. Well, once again, this 1 comes from plugging in the lower limit t prime equals 0, and this comes from the upper limit t prime equals t in the integral. It is easy to see that if you were to take the real and imaginary parts of this expression, you will get Vx and Vy, and from this one, if you did something similar, you will get x and y. And you should verify yourselves that these are exactly the expressions that you are going to get, the ones we have already figured out for Vx, Vy, x and y. Of course, solving this problem in a different manner will not give you a different solution. But I am sure that after you get familiar with this, you will all agree that this method is actually much faster and easier, especially because you are dealing with both components at the same time, as well as the fact that exponential function, the one which you are dealing with in these equations, are of course much easier to integrate and differentiate than sines and cosines. Now that we have two distinct ways of solving these equations, let us now get down to the task of trying to see whether we can get back our special cases from these expressions properly. So these are the x and y components of the results that we have obtained. As always, we are not really going to pay much attention to the z component, which is definitely much simpler than these. Now, let us take a look at the special cases that we had talked about before. One of the special cases we had talked about, the second one that we had talked about actually, was a situation where there was no electric field, so E0 was 0. Now, in this case, the equations for the velocities simply become Vx equals E0 by B0. That definitely is not there because this E0 is 0. Rather, it becomes Vx is Vx0 cosine omega ct plus Vy0 sine omega ct. And Vy becomes minus Vx0 sine omega ct plus Vy0 cosine omega ct. Now, many of you would immediately recognize that this is nothing but the way in which components of a vector transform when they are being rotated through an angle of omega ct. And one easy way to see a consequence of that is if you were to square and add these two quantities, you are going to get simply Vx0 square plus Vy0 square. So this quantity, sum of squares of the two components of the velocity, is an invariant. It does not depend on time. Now that's easy, of course, to understand. We have no electric field here and the magnetic field does no work, so kinetic energy will stay the same. The z component of the velocity stays the same, so the magnitude of the xy component has to stay the same, which is exactly what this statement says. Now, we had also figured out earlier that the motion of the charged particle in this case would actually be a circle. That's the trajectory. So let's see whether our equations, our solutions actually bear that out. In this case, for the coordinates, we get the following. X is x0 plus Vx0 sine omega ct over omega c plus Vy0 by omega c to 1 minus cosine omega ct. And similarly, y works out to be y0 minus Vx0 by omega c into 1 minus cosine omega ct plus Vy0 by omega c sine omega ct. Now, if we move all the time independent terms to one side, we get x minus x0 minus Vy0 by omega c equals Vx0 by omega c sine omega ct minus Vy0 by omega c cosine omega ct. And similarly, for y we get y minus y0 plus Vx0 by omega c equals Vx0 by omega c cosine omega ct plus Vy0 by omega c sine omega ct. And just as we argued for the velocity components, the same kind of calculation here would immediately show you that x minus x0 minus Vy0 by omega c whole square plus y minus y0 plus Vx0 by omega c whole square equals Vx0 square plus Vy0 square by omega c square. So this, as you all would recognize, is the equation of a circle, as we already expect. The center of the circle will be at the coordinates x0 plus Vy0 by omega c and y0 minus Vx0 by omega c. And the radius will be square root of Vx0 square plus Vy0 square by omega c, which is the same as V perpendicular square by omega c. Sorry, not V perpendicular square, but V perpendicular by omega c, where V perpendicular is the magnitude of the component of the velocity perpendicular to the magnetic field. Now notice that not only is this radius exactly what we expect from our previous notions, the calculation that we had carried out physically at the beginning, even the coordinates of the center, these coordinates are also not difficult to understand. If a particle has a velocity with components Vx, Vy, at a point x0, y0, then the arc of the circle that it describes must have a center at a distance r from this point x0, y0 in a direction which is perpendicular to vx, vy. It's very easy to use a bit of geometry to show that this immediately tells us that the coordinates here for the center will be x0 plus vy0 by omega c, y0 minus vx0 by omega c, as we have just calculated. Let us now turn to our next special case, indeed the very first special case that we talked about before, that is where b0 is 0. So let's move this thing out of the way. We are dealing with b0 equals 0 now. Now we must note that the moment we put b0 equals 0, an apparent problem crops up. In many places in these expressions, you will end up with b0 in the denominator, and that appears to give you infinities. So we have to be very careful. We need to be doubly careful actually, because not only is b0 directly there in the expressions, it's also there inside omega c, which, if you remember, is q over m b0. So when b0 goes to 0, so does omega c, and that has to be taken properly into account. To avoid problems with having to treat b0 and omega c together, it's best to actually change everything to one of these. I will choose to rewrite everything in terms of omega c. So Vx here will become E0 over m by q omega c plus Vx0 minus exactly the same thing again, q E0 by m omega c into cosine omega ct plus Vy0 sine omega ct. Now, I need to take the limit of this quantity as omega c goes to 0. Let me just do a bit of algebra before that. If you take the qm by E0 term common, you see you get plus 1 minus cosine omega ct by omega c, and in addition you get Vy0 sine omega ct. Now in this form, it's very easy to take the limit that we need, and the limit is simply going to be, for this one it's going to be 0, and for this one it's again going to be 0. And the easiest way to see that is simply to realize that when omega ct tends to become 0, that is tends to become very small, you can make use of the fact that 1 minus cos omega ct is now 1 minus half omega ct whole square plus higher order terms with higher powers of omega c. So this numerator here essentially behaves like plus half omega c square t square. When you divide that by omega c, the resulting thing is half omega c t square, which vanishes in the limit omega c goes to 0. Of course, I have missed a term here, the term Vx0 cosine omega ct, which in the limit omega c goes to 0 simply gives you Vx0. The other two terms, as we have just established, vanishes. So there is no change in the velocity in the x direction. What about in the y direction? For the y direction, what we need to do is calculate Vy equals minus Vx0 minus qe by m omega c into sine omega ct plus Vy0 cosine omega ct. And here the limit is very, very easy to take. The minus Vx0 sine omega ct of course gives you 0 in the limit omega c goes to 0. Vy0 cos omega ct gives you simply Vy0 in the same limit. So the limit omega c goes to 0, this gives you Vy0 plus Qe by m limit of sine omega ct by omega c, and using the very, very justly famous fact that sin x by x goes to the limit 1 as x goes to 0, it's easy to see that this limit is simply t. So as far as the velocities are concerned, we do get uniformly accelerated motion. Vx stays the same, there is no acceleration in the x direction. Vy increases linearly with time with the acceleration of Qe by m. Fine. So let us now try to see whether the x and the y coordinates also give you the same kind of simple behaviors. So let's just get rid of this calculation for the time being and see. This is just to clear the screen for us so that we can calculate the x and y limits properly here. Now, as far as the x limit is concerned, after you make the same replacement, x works out to be x0 plus Qe by m omega ct plus Vx0 sine omega ct by omega c minus Qe by m omega c square, one omega c from here, another from here, sine omega ct plus Vy0 into 1 minus cosine omega ct by omega c. Now this is actually set up quite nicely for taking the proper limit. You get x0 plus Qe by m omega c m. If you take that common, you actually get omega ct minus sine omega ct by omega c square, taking this and this term together, and then you have Vx0 sine omega ct by omega c plus Vy0 1 minus cosine omega ct by omega c. And we have already seen just a while ago that this limit goes to 0. This limit, of course, is t, and a bit more work is needed to figure out what this limit is, but you should realize that when you expand out sine, the omega ct cancels out, and the term that you're left with is actually minus 1 by 3 factorial omega ct whole cube. So you get omega cube in the numerator, omega square in the denominator. You have 1 omega c left over, so this term vanishes in the limit omega c goes to 0. So the omega c goes to 0 limit for this is simply x0 plus Vx0 into t. This term gives me 0, this term gives me 0. So the x motion is uniform velocity. That's exactly what we expect in this case. There is no force in the x direction. Let us now clear the deck once again to do the calculation for y. Now y in the same limit becomes y equal to y0 minus Vx0 1 minus cosine omega ct by omega c plus E0 by B0, that is Q E0 by m omega c, and another omega c is already there, 1 minus cosine omega ct by omega c square plus Vy0 by omega c sine omega ct. And now the limit omega c goes to 0 simply gives you y0. This term goes to 0. This term goes to Vy0 into t. And the only new limit that we have to figure out is this one. And remember this, if you expand this up to the second order, you get half omega c square t square in the numerator. Divided by omega c square, that gives you half t square. All higher power terms in the numerator will have powers of omega c left over after the division by omega c square. So they will all vanish in the limit. So you get plus q e naught by m into half t square, which is exactly what you would expect when you have a particle moving with initial velocity Vy0 and uniform acceleration q e0 by m in the y direction. So at least in the two special cases where you had either a pure magnetic field or a pure electric field, our complete solution that we have here matches the ones we had already figured out from more elementary considerations. Let us now talk about the third special case, where the initial velocity of the particle was 0. So you had crossed electric and magnetic fields with magnitudes E0 and B0 along the y and the z directions respectively, but you started with a particle which had no initial velocity. So in that case, our motion becomes something like this. The velocity components Vx simply becomes E0 by B0 to 1 minus cosine omega ct, and Vy becomes simply E0 by B0 times sine omega ct. Note that this tells us that initially, of course, Vx and Vy were both 0. 1 minus cosine 0 is of course 0 and sine 0 is 0. As time increases, initially both sine omega ct rises and cos omega ct falls, so that both Vx and Vy increases. But as we also sort of noticed there, Vy will increase faster. For small t, this is like E0 by B0 into omega c t, whereas this is only like E0 by B0 into half omega c square t square. So for very small times, this term is going to be dominating. The particle is going to move upwards with a slight tilt towards the right. On the other hand, as time increases, this thing, the sine, keeps on rising, but then reaches a maximum. The maximum value for Vy is of course E0 by B0, and then when omega ct reaches the value of pi, we have Vy equal to 0. That is where our motion becomes perfectly horizontal. That's the top of my cycloidal motion. By the way, this kind of motion is called cycloidal. At this point, Vy is 0, and then Vx is actually given by twice E0 by B0. And you can immediately figure out that the magnitude of the magnetic force, which is simply Qvx into B0, is twice QE0. This is downwards, so you have at the topmost point a force of twice QE0 downwards in addition to the QE0 upward force which the electric field provides. As we had already said then, at the topmost point the magnetic force is actually twice as big as the electric force. After that, what happens is that the velocity Vy becomes negative, so the particle starts moving downwards. Vx, of course, keeps on being positive throughout. It decreases as omega ct moves from pi towards 2 pi, but only when you reach 2 pi again does Vy and Vx both become 0. Notice that Vx is throughout positive. 1 minus cosine omega ct can never be negative, which means the particle will always have a rightward motion. It will never go back to the left. Whereas Vy goes from positive to negative in cycles, so the particle can go up and down, as we have already seen before. Let's try to look at what this says about the shape of the trajectory. That is, what this says about the way x and y behave. If we, for convenience, take the initial condition to also imply that the particle starts at the origin, that is x0 and y0 are both 0 to begin with, we get from our solution x is E0 by B0 into t minus sine omega ct by omega c, and y is simply E0 over B0 omega c 1 minus cosine omega ct. Now these equations should be quite familiar to people who have studied a bit of geometry, and these are equations for what is called a cycloid. In case you have not seen a cycloid before, let me explain what that is. If you start with a circle, say, of radius r, and suppose it's rolling on a horizontal top without slipping. Now, if you consider a point here is at an angular distance theta from the vertical line drawn from the center, the length of the arc obviously is r times theta. Let us now focus on this point, which was initially at coordinates 0, 0, the point at which the circle was initially touching the horizontal line. Now, as this ball starts rolling to the right without slipping, we will follow the motion of this black dot. Now, notice that as the ball is moving without slipping, by the time the ball turns to an angle theta and this point comes in contact with the ground, the ball as a whole should have translated to the right through the same distance as the length of this arc. That is, it should have translated through r theta. So, the position of the center would be at r theta, r. But this point, the point we are focusing on, is now here, and its coordinates with respect to the center are minus r sine theta, minus r cosine theta. So what are the coordinates of this point with respect to our original coordinate system, where this point, the original point which was touching the ground or the horizontal table, was 0, 0? The answer is simply r times theta minus sine theta r into 1 minus cosine theta. This path, which a point on the rim of a circle traces out as the circle rolls without slipping, is what is called a cycloid. And now, let's go back to our equations. Notice that the equation for x can be easily rewritten as x equals E0 by B0 omega c omega ct minus sine omega ct. So, if you take the radius of a circle to be E0 over B0 omega c and the angle through which the circle turns to be omega ct, this and this together give you exactly the equation for a cycloid. So, the path which our particle traces out is actually the path which a point on the circumference of a circle of radius E0 over B0 omega c would trace out if it were moving with an angular velocity omega and rolling without slipping on a horizontal line. So this is our cycloid path. Of course, other features of the motion, like the fact that y is always positive, so goes from 0 to a maximum value, then comes back to 0, etc., can be easily figured out from these expressions. But what I wanted to emphasize is, whatever physics actually tells us about the way the motion should be, the mathematical calculation does bear this out. Of course, the actual trajectory will be more complicated if you started with arbitrary initial velocities and so on, but that is now something we have already figured out completely, and you can explore how different values of Vx0, Vy0, etc. will make a difference to the kind of motion you have. This is all from me on this particular topic. Bye for now.